by the antenna. Now what happens in an AM receiver? First, let's take the AM wave as it approaches the antenna of our receiver. The AM receiver picks up the waves. First, it amplifies them this way. Them to the demodulator. The demodulator changes the RF amplitude variations back into audio frequency energy. First, in the circuit to take care of bandpass. Now the amplitude limiting part. In place of this IF amplifier, we put a device called a limiter. This takes care of clipping off the amplitude variations that could hash up reception. Alright, the limiter takes care of this. Now, something to take care of our third condition. In place of the demodulator in the AM receiver, we put a device called a discriminator. So, now we've satisfied all frequencies. The bandpass by means of circuit design, the amplitude limiting by means of the limiter, and the translation of frequency variations back into audio amplitude variations by the discriminator. Now we have an FM receiver. But there's a little more to it than just saying we put this here and that there. We want to understand what happens. All right? Here's a simplified diagram of a limiter. It consists of a tuned grid circuit, a resistor, a tuned plate circuit, and bypass capacitors. Also, the sharp cutoff tube. It operates at zero initial grid bias and low plate voltage. Let's see what the action of this limiter circuit is. Here is our FM wave as it leaves the transmitter. It's free of any amplitude variation. But as you saw before, the best laid plans of men and radio go astray, and our wave doesn't stay nice and clean. Amplitude variations creep in, caused by electrical disturbances. So, the wave looks like this when it reaches the antenna of our receiver. The frequency hasn't changed, but there are amplitude variations on the positive portion of the wave and variations on the negative portion. Now let's take this wave through the limiter. The incoming wave induces a voltage in the first tuned circuit. Here, the grid of the tube is connected directly to the tube circuit. Now, with no initial bias, it stands to reason that any positive amplitude swing on the signal will make the grid positive. Therefore, since the grid is positive, it attracts electrons from the cathode of the tube. The electrons move along as a grid current. The more positive the amplitude variation, the more positive the grid will be, and the greater the grid current flow. But the grid current flow through the resistor produces a volt drop which tends to buck the positive signal. Now you can see what's going to happen. As the positive amplitude of the wave reduces, more and more electrons are into the grid. More current flows through the grid circuit.
current flowing into grid resist develops an increased negative voltage that acts against the instant positive state. The voltage drop causes this to finally become so weak it will send further increased on-amp to the grid.
A certain amount gets through. And what happens to the wave? Just this. The amplitude variations on the positive side of the wave are clipped, and with them go the noises they carry. But we still got these to worry about. The negative amplitude variations. The clipping of the negative amplitude swings is simpler than clipping the positive. You've just seen that a positive swing in signal amplitude turns the grid positive. So we'll naturally get a negative grid when the swing of amplitude is negative. And the more that swings, the more negative the grid will become. And what effect does that have? Say the negative amplitude swing is just beginning. As soon as it begins, the grid becomes negative. That means that the grid will repel electrons that try to hop over from the cathode of the tube. Just a small negative charge in the grid means that not all the electrons from the cathode will be repelled. Some will flow through and get to the plate, thus causing a plate current to flow. But as the negative amplitude swing of the signal becomes larger, the grid becomes more negative. It repels more and more electrons that try to get over from the cathode. Now remember, I said we used a sharp cutoff tube in the limiter. The tube is biased very quickly beyond cutoff. Therefore, it will quickly reach the point where its grid becomes so negative that it will repel any electrons emitted by the cathode. We get this effect on the incoming signal. Here's the incoming signal, just the negative amplitude swing of it. As it becomes more and more negative, the action we just went over on the grid takes place. Suddenly, because of the sharp cutoff point of the tube, plate current ceases to flow. And any further negative amplitude variations won't get by. The negative portion of the wave now looks like this. Of course, the negative amplitude swings back up. This means that the grid will become less negative until it reaches a point where the electrons can once more flow through to the plate. Plate current flows again. Now, combine the positive swing clipping action with the negative, and we get this. Here is our FM signal coming in with all its amplitude variations. It gets to the limiter. The two clipping actions we saw take place. First, the positive. The swing goes up and up until it stops, clipped off. Eventually, it starts down again toward the negative swing. It reaches the start of the negative swing and causes the grid to become negative. When the cutoff point of the tube is reached, the negative swing is clipped. The result of these clipping actions is this kind of a wave. Now we have what we went after, a wave with constant amplitude, with all amplitude variations clipped off. The intelligence is still with us, carried in the frequency variations. But we still have a little trouble to get rid of. Notice that the tops and bottoms are squared off. That will mean distortion of the signal. The tuned plate circuit takes care of that. It's able to smooth off any irregularities or sharp corners of a wave by what is called flywheel effect. So the wave that leaves the limiter will look like this. And that's it. Now the wave is ready for the discriminator, the device that interprets these frequency variations as audio voltage variations. Now here's a simplified diagram of a discriminator. It consists of a tuned circuit, a diode detector tube, and a load resistor with a bypass capacitor across it.